2.8, function operations and composition. So we're going to start out talking about function operations, which is basically just doing addition, subtraction, multiplication, and division of functions. Now, this is really nothing new because we've added, subtracted, multiplied, and divided algebraic expressions, right? We did it with polynomials, we dealt with rational expressions, and we've done these things. So this isn't really much different except for that now we're calling them functions. So we're adding this function to that function, or we're subtracting this function from that function. So basically, the functions that we're dealing with are addition, subtraction, multiplication, and division. So if we have two functions, f of x and g of x, then we can add those two functions together. So we say that's f plus g of x is equal to f of x plus g of x. So f plus g of x is equal to f of x plus g of x. So then we're really learning this notation that when we have the f plus g in here, that's saying add those two functions together. Remember, it's not multiplication of f plus g times x, okay? This is just like f of x, where we have f plus g of x, just adding it together. Now, when we're dealing with that, we have to realize that the domain of this combined function is going to be the intersection of the domains of these two functions. Meaning that the only values we can allow to be used here are ones that are valid for both of them. If the function, if it does not work for one of these, then it doesn't work for the addition of the functions. So that's all we have to remember, is that the domain here is going to be the intersection of the domain for those two functions. We can also subtract, so f minus g of x is equal to f of x minus g of x. So again, that's just telling us to subtract two functions. And the domain of this function is again the intersection of the domains of these two functions. So any value that is not valid for either of these functions is not valid for the function, the subtraction function. And then multiplication, fg of x, so that's telling us to multiply the function f of x times g of x. I'm just putting the dot for multiplication there to kind of stress the fact that we are multiplying those two functions. So fg of x, which is kind of interesting because if you look at this, isn't that just the distributive property? If we distribute this through, you end up with f of x, g of x. So it's the same type of thing. And again, we run into the fact that the domain is the intersection of those two functions. So any value that does not work for one of those does not work for the product. And the final one is f over g of x, which is f of x divided by g of x. And let's just put this to be clear that g of x cannot be allowed to be equal to 0. It's in the denominator, so obviously we can't allow it to be equal to 0, otherwise it would be undefined. So the domain of this function, the quotient function, is the intersection of these two functions where g of x cannot be allowed to be equal to 0. So any value that would cause g of x to be equal to 0 also cannot be allowed. But otherwise, it's just the intersection of those two domains. So let's do this. Like I said, you've dealt with this before, it's just new notation. And I actually could have left most of that there, but I'll just erase the whole thing and start further over just to give us more space. So we're going to grab two functions. I'm going to grab two that I've already selected just because it gives a little more variety to it. F of x is equal to x squared minus 3x, and g of x is equal to 4x plus 5. And we're going to find f plus g of x, well, I'll do them one at a time, but f minus g of x, f times g of x, and f divided by g of x, and find their domains. So I guess one of the first things we really want to look at is what is the domain of each of these functions. X squared minus 3x, that's a parabola, and its domain is all real numbers. And then we have g of x is equal to 4x plus 5. That's a line. It's not a vertical line. So therefore, its domain is also all real numbers. So we have that information. So now we know the domain, which means that the domain of this function, when they're added together, will be all real numbers. So I can already put that over there. Domain, all real numbers. So we got that since it's the intersection of those two functions domains. So now we're just going to add them together. So it's x squared minus 3x, and I'm going to put parentheses in here just to clarify that we're taking f of x plus g of x, 4x plus 5. So we have that. Now, obviously, I can get rid of those parentheses and just leave us with x squared minus 3x plus 4x plus 5. Combine like terms, minus 3x plus 4x gives us x. Then we get x squared plus x plus 5. And again, we already said the domain is from negative infinity to positive infinity. So that's all we do, and you've done this before. Like I said, that's just adding polynomials, just adding algebraic expressions. Well, let's go to minus. We've got those functions sitting there already. Let's subtract it. Again, the domain is going to be all real numbers because the domain of each of these functions is all real numbers, and the domain of this composite function, f minus x, I shouldn't say composite function because that has a different meaning, but this compound function, f minus g of x, is going to be equal to the intersection of those two domains. So now we're going to take f of x, x squared minus 3x, minus g of x, 4x plus 5. Here's where those parentheses actually mean a little bit more, because remember, we're going to have to distribute that through. That's one of the reasons you should be careful putting these parentheses in, because it's very easy for someone to accidentally do this. It is equal to x squared minus 3x minus 4x plus 5. If they're just saying x squared minus 3x minus 4x plus 5, and what did we do? We didn't distribute that through. We said this, we meant to subtract the whole thing, but that's not how we wrote it. So that's why I'm very careful about putting the parentheses in and making sure that I follow through with that. So pulling the parentheses out, obviously x squared minus 3x, and then we have to distribute this negative through, so minus 4x minus 5. Combine like terms, x squared minus 3x minus 4x minus 7x minus 5, and now we have f minus g of x, and the domain is all real numbers. Let's multiply them. Again, no restriction on domains, no restriction on the domain, therefore, because it's the intersection of those two domains, so therefore, the domain is all real numbers. Now we have fg of x, so f times g of x. So that's equal to f of x squared minus 3x times 4x plus 5. And I should point out that now we have multiplication. When I did the previous one where I had subtraction, remember that was subtraction. If you have a sign in between the parentheses, in between the two sets of parentheses, that's telling you to subtract or to add. You don't multiply them together. When the parentheses are sitting right next to each other, that's what tells you to multiply. So we have a binomial multiplied by another binomial, so we can use FOIL. So x squared times 4x gives us 4x cubed. X squared times 5 gives us 5x squared. Negative 3x times 4x gives us minus 12x squared. Negative 3x times 5 gives us minus 15x. And then we can combine like terms. So 4x cubed plus 5x squared minus 12x squared gives us minus 7x squared minus 15x with the domain of all real numbers. So again, not too difficult, it's stuff we've already done before. And it is a nice thing with a lot of things that we do in mathematics that it's just reapplying the same thing. What we're really learning here is not how to do the math, we're learning what the symbols mean. So you got fg of x, f minus g of x, that is telling you to subtract, or it's telling you to multiply, or it's telling you to add. So that's all that we're really learning here. Then f over g of x. So now that says to divide. And I'm going to get rid of this domain here because that's going to modify our domain a little bit. Because remember, that's that additional rule that we can't let g of x be equal to 0. So this is going to be x squared minus 3x divided by 4x plus 5. Well, the funny thing with this is we really can't do much with this. This is a prime polynomial, and yes, we could factor this and make it x times x minus 3, but it doesn't allow us to factor anything out, so really, f over g of x is equal to x squared minus 3x over 4x plus 5. So we're kind of stuck there, but what matters now is our domain. We want to say the domain is all real numbers, but we also have to make sure that this denominator is not equal to 0. So we're going to take 4x plus 5 and set it equal to 0. So 4x is equal to negative 5, x is equal to negative 5/4. And by doing that, we see that we cannot allow x to be equal to negative 5/4. So if I want to write that domain, I can go from negative infinity to negative 5/4, exclusive, from negative 5/4, exclusive, to positive infinity, and now we have the domain. We cannot allow x to be equal to negative 5/4 because that would give us a divide by 0. So I hope this helped allow us to understand these things, and realize that with the division, sometimes you'll be able to cancel and you can do the division, sometimes you won't be able to cancel. Or, depending on what those functions are, maybe you have two rational functions. So, which gives you a compound fraction. And you may deal with that and turn it into multiplication. And then you've got to deal with, well, where can I allow it to be 0? Where can't I allow it to be 0? So it can get much more interesting, but that's the same process no matter how we're dealing with it. The next thing I want to talk about is the difference quotient. The difference quotient. Well, talk about using two words that stand for two different operations, right? The difference is subtraction, quotient is division. So the difference quotient is actually finding a difference, subtracting, while dealing with a division. And actually, it is the base of calculus. This is where it all starts, is with the difference quotient. Luckily, you're not going to be going into calculus and dealing that right now, but we will deal with the difference quotient. And the difference quotient is basically a way of combining functions. And I'm going to put this specifically and say, if you have, I should say, if you're dealing with a function and you are looking at 2 points on that function, then we know that we can find the slope or the average rate of change. Right? The difference quotient is really the slope or average rate of change. But there's a little modification to it, that the idea is it gives us the general average rate of change as opposed to a specific average rate of change. Meaning that instead of actually just plugging in two values, 2 points on the function, and find the average rate of change, we calculate or we create a new function, the difference quotient, that will give us the average rate of change for any 2 points. And how we do that is we start with the slope is equal to f of x plus h minus f of x over x plus h minus x. So what we're doing is we're saying if we have 2 points, x, f of x, and x plus h, f of x plus h. We have these 2 points. H is just the distance away horizontally from the first point. So if we add a certain value to the x value of the first one, then when we run this function, we're also going to add that value to the input of that function. So it's just saying if we have a point here, and we have another point here, and that distance horizontally between them is h, then this is x f of x, that point, and this point is going to be x plus h, f of x plus h. That's going to be the other point. So the slope is found just by taking y2 minus y1, so f of x plus h minus f of x, and dividing it by x2 minus x1, x plus h minus x. And if we look at that as it is written here, we can see that we can do a little bit down here. Notice that And since we're dealing with the functions themselves, so f of x plus h, this just kind of has to stay as it is. But we can see that we have x plus h minus x, so it just becomes h. So that's our difference quotient. And you do need to realize that h cannot be allowed to be equal to 0, obviously. So this is just this. We just said, well, we got x plus h minus x. That canceled out, so it's all dependent on the difference in the x values. So we can now put this to use to find the difference quotient for functions. So let me get my paper out of my way. So I'm just going to put that over here so we remember m is equal to f of x plus h minus f of x over h. Now let's say I have the function f of x is equal to 3x squared minus 2x plus 4. So I have a function. Now, if I'm going to do this, that's f of x. Remember, h's can be any number, so it's really just a variable sitting there. And this is f of x plus h. Well, f of x plus h is just f of x, where you plug in x plus h in place of x. So f of x plus h is equal to 3 times x plus h squared minus 2 times x plus h plus 4. And we can go through and try to simplify this a bit. So is equal to 3 times, well, that's the square of a sum. So x squared minus 2x, and I'll do hx. hx plus h squared minus 2 times x plus h plus 4. Distribute through is equal to 3x squared minus 6hx plus 3h squared minus 2x minus 2h plus 4. Excuse me. Gives us 3x squared. Not a lot we can really do with that, right? We have x squared, hx. We don't have any real duplication, so we're going to leave it right there. But that got us into a polynomial. So now we're going to plug this into m equal to f of x plus h minus f of x. So let me just label that clearly as that's f of x plus h. And we're going to go to red again. So this was just, we have f of x and we have f of x plus h. So we're going to plug it into here. So m is equal to f of x plus h is 3x squared minus 6hx plus 3h squared minus 2x minus 2h plus 4. And I know you're looking at this and going, wow, Mr. Davis, that's a lot. I'm dealing with this huge thing. Minus f of x, 3x squared minus 2x plus 4, all over h. Let me just darken that red line there. So all over h. Well, now we can combine like terms, right? We can distribute this negative through and combine the like terms. So m is equal to, well, we have 3x squared minus 3x squared. cancels out. I'm just going to go through and do some other canceling. Minus 2x minus negative 2x. So minus 2x plus 2x cancels out. Plus 4 minus 4 cancels out. Leaving us with 6hx plus 3h squared minus 2h over h. Now you may notice something here. Each one of these terms in the numerator has an h in it. And if you do the difference quotient correctly, that will always happen. This h in the denominator will always cancel out. So if you go through and you find you have a term that does not have an h in it in the numerator when you get done doing this, you made a mistake. So we get to this point, now we can cancel out that h. So that's giving us 6x plus 3h minus 2. So at any 2 points on this graph of f of x equal to 3x squared minus 2x plus 4, you can find the slope or the average rate of change by plugging in x value of the first value and the difference between the first x value and the second x value, or the x values of the 2 points, and it will give you the slope. You don't even have to deal with finding the output of those functions. You just plug it in and I'll get it. And what makes this a basis for calculus is that as h, your distance between the 2 points, gets smaller and smaller and smaller, this leads you to the instantaneous rate of change, or the slope at an individual point on your curve. If we allow h to be equal to 0, then we get 6x minus 2. So if x is 3, we get 18 minus 2, or 16. The slope is 16 at that point. But that's what's really cool about this, is you can go further and further into it and get to that instantaneous slope. But again, remember, we can't allow h to be equal to 0 because we've got to divide by h. But it's leading to the point in calculus where we can do that, where we can get in and say, okay, we can get the slope instantaneously. And that's what this is. This is the introduction to calculus and how it's going to work. And I may point out to you that, you notice this, and I said if h is equal to 0, then this term disappears. So if h is equal to 0, sorry, that's not showing up well. Let me switch to a different color. That marker has finally given up the ghost. If h is allowed to be equal to 0 in this, then we have m is equal to 6x minus 2. Well, the exciting thing about that is, if we take the derivative f of x, or f prime of x, that's not -1, that's f prime, so that's the derivative of f of x, we get 6x minus 2. 2 times 3 is 6. Subtract 1 from 2, we get 1, so 6x. 1 times -2 is -2. Subtract 1 from 1, you get 0. -2. And constant disappears when you take the derivative. So that's where we're getting to, and that's why the difference quotient is so important, because it is the basis of calculus. But at this point in time, we can take any function and plug it into this difference quotient and get the slope, given a formula for the slope, given any x value for a single data point, and the distance to the next x value you want to look at, and it'll give you the slope. So that's pretty cool. The last thing we want to cover, so there's one more thing in this, is composition. Sometimes referred to as composite. So that's why I said I have to be careful about saying composite function. They were compound functions. So composition. Remember, this is function operation, addition, subtraction, multiplication, and division. The difference quotient, where we're finding the difference and getting the slope by taking the quotient. And composition. Composition is put F with a little circle. It kind of looks like a degree symbol, but midway through. It's not a multiplication symbol, that's not a filled in dot, it is an open dot. And that is said F composite G of X, or F of G of X, which when you say F of G of X, it starts to help you to understand what that means is you're taking F of G of X. So all you're doing with the composite function, with composition, is you're taking the one function and putting it as the input to the other function. And that's all you're doing. So not bad. Well, let me grab a couple functions to work with here. Let's say f of x is equal to the square root of x plus 4, and g of x is equal to 2 over x. So if that's the case, and we want to find the f composite g of x, or f of g of x, we're just going to, so I'm going to put that down here so we're clear what we're working with. And it does tend to look like you're writing fog. Such is not the case. You have to make it a little smaller so that it's obvious that it's not an O. F of g of x is equal to, we look at f of x and we're just going to plug g of x in place of the x in there. So the square root of 2 over x plus 4. And that's it. That's composition. We can do it the other way. G of f of x. So now g is going to be the main function. We're going to plug in f of x in place of x. So we have 2 over the square root of x plus 4. So the main function is 2 over x, and we're plugging in f of x, the square root of x plus 4, in place of x. Well, how does this affect us for domain? Basically, what we run into here is that our domain must be as any domain, any value of x that's valid for the inputs. In this case, we're talking f of g of x. So we're looking at the domain of g of x, and we have to make sure that the output of g of x fits the domain of f of x. So it's one of those things where you kind of have to play with it a little bit. Many times we have things where there's no limitations caused by that, but we may. In here, we find out that x plus the square root of x plus 4 has a limitation that x cannot be less than negative 4. Because if it goes less than negative 4, then we're taking the square root of a negative number, so we can't do that. So let's give me my domains here. So the domain of f of x is x greater than or equal to negative 4. It can be negative 4. Negative 4 plus 4 is 0, and the square root of 0 is 0. So we can do that, but it can't be less than negative 4. For g of x, x can't be equal to 0. That's the only limitation on that. So we know that we can't allow x to be equal to 0, but we also can't allow the output of this to be less than negative 4. So what's going to make this output less than negative 4? Well, let's look at it. 2 over x. What value of x is going to make this, let's just look at it. What value of x will make this equal to negative 4? If x is equal to negative 1/2, then we're going to have g of x equal to negative 4. That's okay, but which direction do we need to go here to cause a problem? Well, if it's going to make it larger, right? And how's it going to make it larger? Well, if this gets smaller, then that's going to make this larger, right? If I have 1/3, then this is going to negative 1/3, that's going to become negative 1/6. So I shouldn't say it makes it smaller if the absolute value of this is smaller, but it's negative. Positive values aren't going to do anything to us. Any positive x value will work great. But if we have anywhere from negative 1/2 to 0, this is going to get too big. So our domain of f of g of x is going to be from negative infinity to negative 1/2 inclusive, because remember, negative 1/2 puts us at negative 4, and that's okay. And from 0 exclusive to infinity. And that will be the domain of that function. For this one, what do we run into? Well, g of x cannot be equal to 0. So is there any value here that's going to cause this function to be equal to 0? Well, if you take 2 and divide it by any number, there's no number that can turn it into 0. So we don't have any limitations on what can come into this function g of x, because we can't, there's no limitation on what, x cannot be equal to 0, but there's no way, well, sorry, let me change that. X can't be equal to 0, so I can't allow the square root of x plus 4 to be equal to 0. So that's going to be my limitation. And how is the square root of x plus 4 equal to 0? Well, when x is equal to negative 4, so I can't allow x to be equal to negative 4. That's the limitation put in place by g of x. And remember, the limitation on f of x is that x can't be less than negative 4. So simply, the domain of this one is from -4 exclusive, because we can't allow it to be -4 and we can't allow it to be less than -4, to infinity. Any other value can work. As long as this stays positive, then we're okay. So that's finding our domain of composite functions. Last thing I want to do, I just want to erase this and go into one final thing with these composite functions, is just determining the functions that could create a certain composite function. And this is really one of those things that many times there's multiple answers that could be used. But just if you're given the function f composite g of x is equal to the square root of x plus 2 over 3. And I say, give me f of x and g of x of that composite function. We're just looking for any functions that we can use that allow this to work. So I could say that f of x could be the square root of x over 3, and g of x is x plus 2. Because when I plug x plus 2 in place of x, then I get x plus 2 over 3, square root of that. So that works out. And that's all you're really looking for with this. You're looking for, is there a function that will work with this? I could also do this. That's one possibility. I could say f of x is equal to the square root of x. And g of x is equal to x plus 2 over 3. That would also be valid, wouldn't it? If I plug x plus 2 over 3 in place of x, I get the square root of x plus 2 over 3. And there are other ones we could come up with, because we could even look at this and say, well, isn't that the same as the square root of x over 3 plus 2/3? So therefore, I could say f of x is x plus 2/3, and g of x is x over 3. So lots of different possibilities. The goal is just to come up with two functions that, when you do the composite, gives you that final result. And that finishes it up, section 2.8, function operations and composition.